All right, I think we're just about ready to get started. Thank you everyone for joining us, and anyone who might be joining us online, welcome. I'd just like to take a second to introduce Dr. Roger Atkinson to us. He's Professor Emeritus at the Air Pollution Research Center at the University of California, Riverside. Roger received his PhD in physical chemistry at the University of Cambridge and was a postdoc in Ottawa and in Toronto at the National Research Council and at York University, my personal stomping ground. Following that, he moved to the Air Pollution Research Center at UC Riverside. And other than a short time at Shell Research in the UK and at ERT Inc. in California, he was a research chemist and then a faculty member at the Department of Environmental Sciences at UCR. Dr. Atkinson has authored more than 350 papers, books, chapters, and reports, and has served on numerous state, national, and international air pollution committees and advisory panels. He was elected as a fellow of the American Geophysical Union as well in 2005. His work is focused mostly on the kinetics, products, and mechanisms of gas phase reactions of VOCs, and we're not only grateful for the monstrous body of work that he's contributed in this field, but also that he was willing to join us here today to present some of his work on OH-furan reactions and their implications for aromatic hydrocarbon degradation. So, thank you.
Thank you for the kind introduction, and thank you for sort of having me here. All right, so I'll get going. I'm actually going to try and talk about two different things, one of which will be the furans and the other will be on nitro-aromatic formation in the atmosphere. Can you really form them from gas phase reactions? So background, aromatic hydrocarbons comprise about 20% of VOCs in gasoline and in vehicle exhaust in the US and in non-methane VOCs in urban areas. They react dominantly with OH radicals. The NO3 radical reactions, which I'll mention later, are very minor. And the OH radical reactions proceed by initial addition to the aromatic ring and to a much lesser extent by H-atom abstraction from the alkyl substituent groups. And I'm going to use this for my pointer. So most of the reaction forms these OH aromatic adducts, which are these guys here, and less than 10% of the reactions for toluene, xylenes, and trimethylbenzenes goes by H-atom abstraction to form the thing up on the top right. So since about 1990, mainly through work from Cornelius Zetschi's group in Germany, it's been known that these OH aromatic adducts can react with oxygen and with NO2, and that these two reactions are competitive. So the O2 reaction, the one on the left, leads to products including ring cleavage compounds, 1,2 dicarbonyls and unsaturated 1,4 dicarbonyls that I'm going to talk about in the next few minutes. And the NO2 reactions can lead to products including nitro-aromatics, which I'll try and cover at the end point. And Cornelius Zetschi's group has measured rate constants for the reactions of O2 and NO2 with these OH aromatic adducts for benzene, toluene, and some of the xylenes. And the two reactions are of comparable or of equal importance in air at NO2 concentrations of ranging from about 1 part per million for benzene up to several parts per million for toluene and the xylenes. So clearly, unless you're in some horrendously polluted atmosphere, these OH aromatic adducts are going to react dominantly with O2. And I'll give a simplified scheme here for the reactions of the OH toluene adduct with O2. I've left out, there's another potential pathway leading to formation of epoxy compounds, which seems to be probably about a 20, maybe 30% pathway, but they've never really been identified. For the part that I'm going to talk about, the important ones are the formation of these, of the peroxy radical, that's this guy, which is formed by a reversible reaction with O2. The thing can back decompose, can react with NO to form the products, which are the di-unsaturated dicarbonyls, C6 or above, or undergo a cyclization reaction to lead to these bicyclic radicals, that's these, which then go on to react to form what is shown as methyl glyoxal and 1,4-butene-diol. So methyl glyoxal is this, 1,2-dicarbonyl, and the 1,4-butene-diol is one of my unsaturated 1,4-dicarbonyls. The system or the kinetics are such that the pathway with with NO of that peroxy radical is only important at part per million concentrations of NO, so we can essentially forget about that for urban areas or for the atmosphere. And the other thing is that if you add the OH at different positions on the toluene, you will get nominally, if you go through this reaction scheme, different sets of 1,2 plus 1,4-dicarbonyls, and the other set you can get is glyoxal plus what is 4-oxo-2-pentanal. And I'll try and give a few more details here. This is sort of this is adding OH to metaxylene, and I've added it very craftily at a position which is symmetric, so there's only one set of products. So we get our bicyclic radical. That's this guy. It can add O2 to form a bicyclic peroxy radical. That will react with NO in the presence of NO, when NO is present, to form the bicyclic alkoxy radical. This guy can also form a small amount of nitrate, where you convert the OO in the peroxy to an ONO2 group. And the further reactions of this bicyclic alkoxy radical give rise to what in this case is, again, the 2-oxo-4-pentanal plus methyl glyoxal. And if this reaction scheme is correct, which is always a possibility that it isn't, then one would expect identical yields of the 1,2-dicarbonyls, that's these guys, and the unsaturated 1,4-dicarbonyls. I should point out that none of these unsaturated 1,4-dicarbonyls are commercially available. Nearly all of them don't. There's one of them which will gas chromatograph or elute from a GC column without prior derivatization. The rest don't. So they're not exactly easily amenable to analysis. So this is sort of trying to look and see whether or not the data support the equal yields of the 1,2-dicarbonyls and unsaturated 1,4-dicarbonyls. The black bars are the 1,2-dicarbonyls, glyoxal, in this case, methyl glyoxal, biacetyl in this panel. And the colored bars are the proposed co-products to those 1,2-dicarbonyls. Two of them are mentioned as shown, or at least labeled, so the different colors refer to different unsaturated 1,4-dicarbonyls. It had been known for a number of years because 3-hexene-2,5-dione, that's the green one, that can be readily gas chromatographed or analyzed by GC without derivatization. It's been known that its yield from paraxylene is equal to that of glyoxal. It was done by Rainer Vokemer, who's at U of Colorado now, and we've got the same numbers, and we've also shown that the methyl glyoxal and 3-hexene-2,5-dione yields from 1,2,4-trimethylbenzene are identical. And we have some GCMS data of derivatized 1,4 on saturated 1,4-dicarbonyls, which are all the other colored bars. And the ones that you can see, the blue ones, the blue compound, which is 1,4-butene-diol, does indeed appear to be formed in the same yield as its co-product. From toluene here, to methyl glyoxal from toluene, and to biacetyl from orthoxylene. But the rest of them, it doesn't look quite so happy a story. Clearly they're formed or appear to be formed in significantly lower yields than the 1,2 dicarbonyls. So is this an analytical problem? So the first section there is just saying what I'd said. So it could be an analytical problem. We aren't able to analyze very well some of these 1,4 dicarbonyls. It could be the fact that in chambers, which I'll show you in a moment, some of these unsaturated 1,4 dicarbonyls are being very rapidly lost by photolysis, wall losses, or OH radical or something else. And of course, as I mentioned, it's possible that the assumed mechanism is incorrect, but then it's not easy to see what else is going on. And it's been known for a number of years that these unsaturated 1,4 dicarbonyls are major products of OH plus furan reactions. And since the furan reactions seem to be a little simpler in their mechanism, we decided to have a look at those. So we looked at products from furan, furan D4, 2 and 3 methylfuran, and 2, 3, and 2, 5 dimethylfuran. We've done the kinetics of them, and that was published a couple of years ago. The furans are fairly rapid reacting, which is sort of nice because that limits the extent of secondary reactions of the products. But anyway, off we went. So our experiments are carried out in essentially 7,000-liter Teflon chambers. This is sort of one of them. This wasn't the one that we actually used, but we had a couple. The other one is interfaced to a direct air sampling atmospheric pressure tandem mass spectrometer, or API MSMS. And most of our analyses are by gas chromatography or they're either by gas chromatography or by API MSMS. For the work I'm going to talk about here, we generated OH from photolysis of methyl nitrite, same way that Jeff does some of his. Nice, easy way of generating OH. You can make methyl nitrite, store it quite happily for a long period of time, and it seems to be fairly straightforward. Our initial concentrations of things were about 5 parts per million by mixing ratio of methyl nitrite and NO, and about a ppm or so of the furan. And in a number of experiments, and you'll see why, we added 2,5-hexane dione as an internal standard at a lower concentration, about 300 parts per billion. And for the API-MS experiments, we used significantly lower initial concentrations. So I'm going to talk about the API-MS first. So we use either positive ion mode, where it's H3O plus water clusters as the ionizing or the reagent ion, or conditions where a negative ion, where the major ions are O2 minus, NO2 minus, or NO3 minus. And I'm only going to show data for positive ion. The negative ion was, you'll see what that showed later on. So just as an example, this is OH plus 2,5 dimethylfuran. We see a series of peaks, positive ion mode, and once you've, at least under the conditions we run it, you generally form protonated molecules or protonated homo or heterodimers. And in some cases, you get water adducts. And once you've done this for months on end, you get a pretty easy hang of how to do it or how to interpret it. I should point out that the peak identifications or peak attributions are based upon MSMS analysis of the peaks seen in the API-MS. So we can do MSMS fragment ion spectra. So the 113 we interpret as 112 plus H plus, 115 as 114 plus H plus, 129 is 128 plus H plus, 131 is a water adduct of the 113, and the 133 is a water adduct of 115, and then 225 is 112 plus H, and so on. And so all these are nice and easily done. If you do the MSMS spectrum of the, let's say the 225, well, let's say take 227, you would see a large peak at essentially two fragment ions, one at 113 and one at 115. So it's 114 plus 112 plus H. And so really out of this we get three obvious products of molecular weights 112, 114 and 129. And you can do them for all of them. This is the positive ion of all of them. The furan, obviously, nice and simple, products of molecular weight 85 and 100. The 119 is just a water adduct. The ones out on the 185 and 201 are homo and heterodimers. And similarly down here, 2-methylfuran or 3-methylfuran, molecular weights 98, 114. That's it. And then the others have an extra, 2-methylfuran has an extra product of molecular weight 100, and 2,3-dimethylfuran has 112, 115, and 114 and 128. This is an NO plus adduct of the furan, dimethylfuran. Can't be that. Can't remember what it is. Okay, this is what we see, the bottom line, or what we get out of these. The molecular weights are given there. The ones in red are the unsaturated 1,4-dicarbonyls. The ones listed in blue are observed in both positive and negative ion mode. We observe the 1,4-dicarbonyls only in positive ion mode. And the 128 from 2,5-dimethylfuran is observed only in positive ion mode. So that the positive and negative tell us something, or at least give us some indications. And you won't be able to read this probably, but this is a reaction scheme we put forward. The OH adds typically to the 2 or 5 positions, and it's was being proposed since the first work by Ian Barnes's group, that they ring then fragments, and you can get a series of reactions going without the involvement of NOx to form the unsaturated 1,4-dicarbonyl. So this is pathway A, will give the unsaturated 1,4-dicarbonyls. What we found is that the yield of the 3-hexane 2,5-dione from OH plus 2,5-dimethylfuran was higher in the absence of NO than in the presence of NO. About 34% in the absence of NO, 24% in the presence. And so we came up with this sort of proposed reaction scheme. Molecular weights of the products out of C and B are essentially identical, and you get different products depending on whether the OH adds at the 2 position or 5 position in some cases. And reaction pathway D, the one on the right, which gives a carbonyl ester, is only observed, or we can only discriminate it in the case of OH plus 2,5-dimethylfuran. It's definitely not formed from the furan D4 reaction because the deuterated, or the mass peaks are incorrect or don't fit it. And the product masses for all the rest of them, this channel would be the same as these 2 channels, or one of those 2 channels. So you really couldn't tell. And the interesting one is the products that would come from these 2 channels, which are either acids or sort of hydroxy substituted furanones, are the ones that are observed in negative ion mode as well as positive. The others are only observed, i.e. the unsaturated 1,4-dicarbonyls, and the carbonyl esters are only observed in positive ion mode, at least if these schemes are correct. So the rest of it was done by gas chromatography. You can do the furans and the hexane dione internal standard just by collecting them onto 10x solid adsorbent and doing GCFID. No derivatization needed. Nice and easy. That's the way we typically do things. But for the rest, we did we sampled post-reaction onto an annular denuder for 60 minutes at 15 liters a minute, so that's about 900 liters. We've got plenty of reaction chamber or chamber volume, so that wasn't a problem. The denuders are coated with an XAD resin and then further coated with pentafluorobenzyl hydroxylamine. And that allows us to derivatize sort of in situ any carbonyls to form oximes. Then you can do analysis by GCMS and GCFID. So the oxime formation is shown in this one. This is the pentafluorobenzyl hydroxylamine. It forms an oxime, and there are syn and anti forms of these oximes. For a carbonyl with a double bond, you can get a total of 8 isomeric oximes. If it's symmetrical, you can get 6. So you get a large number of peaks of these oximes for a given carbonyl. And this is orthoxylene on the top. It's an OH plus paraxylene. That's known to give, known it for a while, that gives 3-hexene 2,5-dione. And the analysis with the denuder system gives us these 2 oximes. These are assumed to be cis. Well, in fact, they're known to be cis from GCFID analysis without derivatization. So those are the cis ones. We had a trans 3-hexene 2,5-dione custom synthesized for us, and that's this one. And clearly that's all very, very pleasant. At least it seems to be completely trans, as opposed to the product we get out of OH plus paraxylene. And the OH plus 2,5-dimethylfuran gives us a mixture of cis and trans. And from GCFID analysis without derivatization, we get 1 peak for the cis, 1 peak for the trans, and essentially a 70-30 cis-trans mix. So all well and good, but rather interesting that the dimethylfuran gives you something which is not cis. And in fact, even more interesting, and this was noted or mentioned by, or noted, observed by Ian Barnes and his group, and in the 1994, and by Gomez Alvarez in, I think, 2006, that 1,4-butyne-diol from furan is formed almost totally in the trans form. It's sort of an interesting one. So on the top 2 panels, the second one is a OH plus orthoxylene, which gives rise to 1,4-butyne-diol, and that's at the M plus H plus of the oxime. And clearly, if this is cis, this one is mainly trans. And then for the next one down, which is 2-methylfuran, OH plus orthoxylene also forms that. So if you're at the right mass at 489, you see that one, or the oxime of that. If this is cis, then this one is a cis-trans mixture and maybe mainly trans. And again, that's actually in agreement with what Gomez Alvarez observed using solid phase microextraction fibers also coated with the pentafluorobenzyl hydroxylamine. So that's all fine and well. We see these things. We can tell to some extent whether this formed initially as cis or trans, but we'd like to quantify them. So what we did was use the 2,5-hexane-dione as an internal standard. We have its concentration, can be measured readily by FID without derivatization. Luckily, the furans are reactive enough. They're about 6 to 20 times more reactive towards OH than the 2,5-hexane-dione. So we can put the 2,5-hexane-dione in prior to reaction. There is some reaction of the 2,5-hexane-dione, but it's relatively small, and luckily its products don't interfere. So from a measurement of the hexane-dione after reaction, we measure it before and after, but from the one after, and we can get the ratio of the unsaturated 1,4-dicarbonyl to internal standard from GCFID measurements of their oximes. Generally, nearly always dioxenes. There were a few monooxenes formed, or small amounts formed from 3-methylfuran and 2,3-dimethylfuran. We took those into account. So then we can get a number or a concentration of the 1,4-dicarbonyls after reaction. And so this is a GCFID of the denuder sample after reaction. You can see IS is the internal standard. There are 3 oxenes of it. You could expect, I think, 4. You see 3. The other is either not present or it's incorporated in one of the other peaks. And then the ones at the right. These are the 1,4-butyne-diol that I showed previously. The other peaks we can identify. 2 or 3 little peaks in there are from the product from OH plus 2,5-hexane-dione. We've identified that compound. It's 3-oxo-butanal and then glyoxal. And some of these others are from the derivatizing agent. So we can account for pretty well everything. I should note that pretty well every experiment we do, we see small amounts of glyoxal. It's almost ubiquitous. It's probably a second-generation product in most cases, but it's nearly always present at low levels. Then we need to account for photolysis and losses of the unsaturated 1,4-dicarbonyl. So wall reactions, photolysis, and OH reaction. Some kinetic data are available for 1,4-butyne-diol, the 4-oxo-2-pentanal, and the 3-hexane-2,5-diol. The latter, as I've mentioned, can be analyzed with GC without derivatization. But we also get some data, or have some data, on the time concentration behavior of these unsaturated 1,4-dicarbonyls during our reactions, and that can be quite useful. So if you look at sort of A reacting to give B reacting onwards, there's a nice, from consecutive reaction theory, there's an analytical expression relating the concentration of the product to the extent of reaction. So this is our product. This is our extent of reaction. It's defined as the ln of furan at initial divided by furan at times t. And you get a series of curves. You can calculate a series of curves depending on the rate constants K2 over K1, or rates K2 over K1. K2 is the loss rate for the product, in this case the unsaturated 1,4-dicarbonyl. K1 is the loss rate of the furan. So if there are only OH reactions, then K2 over K1 is just the rate constant for the product divided by the rate constant for the furan. If there's no reaction, it would go up and finally plateau off. Rapid reaction, go up rapidly, and disappear off quite rapidly. So you can get some sense of is the observed behavior consistent with a given rate constant or given loss rate? And in this case, the data are well fit using the experimental or the literature values for the OH rate constant for 1,4-butyne-diol. That was published in 2013 by Martin et al. From Spain. And the photolysis rate is from Ian Barnes's group in Germany. I guess one of it was from the Urifor chamber or they used the Urifor chamber in Valencia. And if you put their data in, you get the rate ratio K2 over K1 to be 1.03, and that clearly fits the data reasonably well. I should mention that we don't have any real constraint on the vertical axis, but we just fit it visually. But certainly the trend with extent of reaction fits the data. And we did a whole series of experiments using API-MS, where we have continuous irradiation, continuous reaction. We lowered the light intensity by a factor of 4 from the denuder experiments. The API-S has a sort of cycle time, the way we do it, of about 3 minutes. You can take a spectrum every 3 minutes. And so we did that during the experiment. This assumes a constant OH. It was undoubtedly decreasing slightly, but not very much. And again, you've got these K2 over K1, the ratio of the loss rates of the product to the furan. Because of the lower light intensity, if the fit of 1.03 on the last slide would now become about 0.9, and the data are fit pretty well by somewhere around 0.8 to 0.9. So everything's looking reasonably consistent. And I'll show only one more. 3-methylfuran, this is the denuda samples. We had 4 experiments, 1 data point per experiment, and they well fit using, an estimated rate constant for OH plus this compound, which I guess is 3-methyl-1,4-butyne-diol. I estimated, based on sort of structure reactivity considerations and the data for some of the other 1,4-dicarbonyls, estimated a rate constant of about 6 times 10 to the minus 11, and assumed a photolysis rate relative to JNO2 of about 0.2, based on the German data. As I'll mention in a moment, photolysis was pretty unimportant in our system. And again, that way, that gives you a pretty good fit. And the dashed line gives you some sort of idea of how sensitive the system is. It's not fantastically sensitive, but you can certainly tell within better than a factor of 2 what the loss rates are. And so these seem to fit all our data. The numbers, this one, it's literature data. It's actually measured data that's in the literature. This one again is in the literature, so that's from OH, would be from OH plus 2-methylfuran. I estimated the rate constants for the ones from 3-methylfuran and 2,3-dimethylfuran, and made guesses on what the photolysis rates are. These we'd measured previously in our laboratory. This is for the cis-trans mixture that we see in the reaction, and we have shown numerous times that with black lights you don't photolyze 3-hexene-2,5-dione. You can just leave it for an hour or more with black lights and there's no loss. It just sits there quite happily. You do get cis-trans isomerization, but you get no actual loss of 3-hexene-2,5-dione. So these photolysis rates are for loss of the compound, not for cis-trans isomerization. So the data are all fit by fairly reasonable numbers. These are sort of what you would expect for the structure of the compound. The correction factors for secondary reactions were relatively small, biggest for 1,4-butyne-diol from furan, so that the correction factors increase with the extent of reaction and with the increase with the value of K2 over K1, i.e. how reactive the product is divided by how reactive the starting compound is. And some of them are getting down to not too bad. This is much better than the aromatic systems, which are the aromatic hydrocarbons are generally less reactive than the furans, so the correction factors, unless you're at really low extensive reaction, will be quite high. And photolysis was under our conditions. Our OH concentrations are about 10 to 20 times ambient. Our photolysis is about 5 times less than ambient. So we're really pushing it, skewing the system towards OH reaction. So if photolysis was important in our system, it would be dominant under atmospheric. And in fact, I think even for most of these unsaturated 1,4-dicarbonyls, photolysis would dominate in the atmosphere. The other thing is black lights, which we use, essentially don't have any intensity beyond about 400 nanometers, which is where these compounds continue to absorb and undergo photolysis. So the yields that we get 75% of the butene-diol from furan. That's certainly consistent with the literature. The ones labeled A are from Ian Barnes's group. with FTIR, in situ FTIR spectroscopy. Their calibration was based upon or Ernie Twizon from our lab, his CO stretch intensity for 3-hexane-2,5-dione. So they're based upon a sort of literature value for the intensity of the CO stretch. The others, the ones labeled B, are from Gomez-Alvarez et al., who use solid phase microextraction fibers coated with a derivatizing agent. And they had one standard, which, if I remember rightly, was the trans of this one. And so they were able to do a calibration for that. They assumed that collection and derivatization efficiency was the same for the cis of this and also for that. And that's a bit dodgy because the solid phase microextraction fibers is a mass transport onto the fiber followed by derivatization and then ultimately GC, FID. And we found that adding a carbon made a factor of about 2 difference in the collection on an homologous series, factor of 2 difference in collection and derivatization efficiency. So this one, undoubtedly perfectly fine. This one may be a little dodgy, and this one may be a bit dodgy. So who knows? And then there's the 1.4% there from Tapia et al., and they decided to do it without derivatization and assumed that they would actually be able to measure these compounds. Apparently doesn't seem to be the case. I'm sort of a bit taken aback by that one, but anyway, you know. Admittedly, I could sort of mention that, gee, well, we're okay, we're in the middle between these, but I don't know. Anyway, we did, for 2,5-dimethylfuran, we did only one experiment with the denuder sampling, which gave us the 27%, and we'd done a whole series with GC analysis without derivatization, which gives us a 24 plus or minus 3, so everything seems to hang together. So I'm pretty sure of this one and this one. And then the question comes about what are our data like for the others. We did some control experiments. We decided we'd better use this technique to look at glyoxal from 3-methyl-2-butenal, the compound up in here. We got 40%, and that's in almost perfect agreement with what we'd previously done using in situ FTIR spectroscopy. So at least the collection and derivatization efficiency of glyoxal and 2,5-hexane-dione seem to be the same. And we showed that was also true for a series of other carbonyl compounds, fairly simple carbonyl compounds. We saw no evidence for wall losses of this unsaturated 1,4-dicarbonyl from OH plus 2,3-dimethylfuran. In most of our experiments, the denuder extended, well, in all experiments, the denuder entrance extended into the chamber, so there was no sampling upstream of it, no sampling line. But in this one, some of these, we did some preliminary experiments where we added the 2,5-hexane-dione after the reaction, and it turned out that we then had to wait up to about 2.5 hours before starting the denuder collections. And we got the same numbers as when we started them immediately. So it doesn't seem that there was any significant wall losses. And the API-MS data indicated that there was no rapid wall losses of any of these unsaturated 1,4-dicarbonyls. And we looked at what happened when we did an experiment. We can very rapidly pump away a large fraction of the chamber volume and then backfill with pure air and see whether there was any partition into the wall of these compounds, and did it then slowly come back out. And at least for this one, oh well, it's the only one we looked at, which, you know, because that had the lowest yield of any of them from the furans, and we saw no evidence for stuff coming off. So we're left with the conclusions that there are clearly products other than unsaturated 1,4-dicarbonyls. The API-MS clearly sees that. Paul Zeman did some aerosol work on these, looking at aerosols, and clearly saw some aerosols which had the compounds, in fact, which we saw by negative ion APIMS, or looked like derivatives of those to be present. The yields do seem to decrease as you add number of methyl groups around the furans, since the data for 2,5-dimethylfuran doesn't have any obvious reason to be low. But the question still comes, do we have problems for these others? For the unsaturated 1,4-dialdehydes other than 1,4-butenediol, and for all of the unsaturated ketoaldehydes. I have no idea. Our data does suggest is suggestive that we may have problems, but I don't know. And if we do have problems, it's clearly not due to rapid loss processes that were unexpectedly high loss processes of these 1,4-dicarbonyls. So to some extent, we don't really resolve anything on the aromatics, but at least we seem to have an idea that they're not being rapidly lost under our conditions. So I'm going to stop the first one there. And the people I'm going to acknowledge is Janet Airy, who sort of keeps me honest on analytical techniques. The experimental work was funded by US EPA, and the experiments that we carried out were done by a grad student, Noriko Nishino, and a staff researcher, Sarah Ashman. And I will then, doing okay, talk about some formation of nitro-aromatics in the atmosphere. So mainly PAHs, although I will mention monocyclics, but it sort of goes back to PAH chemistry. So there are these 4-ring PAHs, pyrene, which is this guy, and it's isomer fluoranthene. They're emitted into the atmosphere from combustion sources. They're present mainly in the gas phase at normal temperatures. I mean, somewhere Southern California, they're about 90% gas phase, molecular weight 202. But out of, if you take samples, you observe they're nitro derivatives, so nitrofluoranthenes and nitropyrenes. Emission sources are generally one nitropyrene, essentially only one nitropyrene, a little bit of 3-nitrofluoranthene. So if you take a GCMS analysis at 247, M over Z 247, the molecular weight of these nitrofluoranthenes and nitropyrenes, you see one nitropyrene. It's the electrophilic nitration product of pyrene. It's also genotoxic, so that's why there was a lot of interest in these compounds. But if you look in the atmosphere, take an ambient sample, these are present on particles, take an ambient sample, you see one nitropyrene, but you also see 2-nitrofluoranthene, 2-NP, and 2-nitropyrene. These analyses were conducted on different columns, so that's why the retention times don't match. But almost always you see more 2-nitrofluoranthene in the atmosphere than 1-nitropyrene. And it's not emitted. There is one strange emission source which gives 2-nitrofluoranthene, and it's a carbon electrode plant in Italy, somewhere in Milan, Italy, was found to produce the stuff. But nobody else has ever seen it in anything but really, really minute amounts relative to 1-nitropyrene. And Nielsen et al. From Denmark proposed how you would form these in the atmosphere. You add the OH to the most electron-rich position, which in pyrene, the one shown, is the 1 position. Add the NO2, ortho to it, 2 position, eliminate water, and off you go. And similarly for 2-nitrofluoranthene, the OH would add at the 3 position, NO2 goes on at the 2, kick off water, and you've got 2-nitrofluoranthene. So this has been sort of known for 20-odd years, sort of that these compounds, these 2-nitrofluoranthene, 2-nitropyrene, appear to be able to be formed from gas phase reactions in the atmosphere. And there are similar ones for other PAHs. These are dimethyl nitro-naphthalenes from dimethylnaphthalenes. Dimethylnaphthalenes are all in the gas phase. we can do chamber experiments exposing them to OH radicals or NO3 radicals. And we did, I think this was in probably 2003 or 1996, I can't remember, but there was some big field study in the LA area, and we took samples at Azusa, which is relatively close to downtown, Riverside, which is about 60 or 70 kilometers downwind, and Bannon, which is not quite out in the boonies, but a bit further downwind, almost out to Palm Springs. And what you see is that the one in Azusa fits with the chamber OH, and there are the two major compounds I'm going to talk about are 1,7-dimethyl-5-nitronaphthalene and 2,7-dimethyl-4-nitronaphthalene, so 2,7,4 and 1,7,5. And as you work your way downwind, the ratio of those two changes quite significantly. The top one looks just like an OH radical exposure, or I should have mentioned there are something like 12 of these dimethylnaphthalenes, and there are and 56 dimethyl nitronaphthalenes and ethyl nitronaphthalenes, and they don't all resolve, as you can see. So it's a sort of unholy mix, but you can sort of look at the profiles, and there's really distinct changes. And this one is getting fairly close, reasonably close to what happens in the chamber if you expose them to NO3 radicals. So as you're going downwind, you see in more NO3 chemistry than OH chemistry. And it would be rather nice to see if you could really, if those would fit with our chemical understanding or kinetic understanding of these reactions. So if you go back to just loss rates, these are calculated lifetimes for benzene, toluene, xylenes, trimethylbenzenes, and naphthalene and dimethylnaphthalenes. I've used 2 times 10 to the 6 as the daytime OH and 5 times 10 to the 8 molecules per cc as the nighttime NO3. And you can see that they all obviously react with OH, and the OH radical reaction dominates. NO3 is really very minor as a loss process. As you'll see in a moment, hopefully, the NO3 plus naphthalene and dimethylnaphthalenes, the rate constant depends on NO2. So these numbers for those were at 100 ppb of NO2, which is a bit on the high side. But anyway, dominant reactions OH, NO3 is a minor loss process for these aromatic compounds. So mechanism for OH, same as I had before. So if the nitro-aromatic is formed from the NO2 plus the OH aromatic adduct with a yield of alpha, the nitro-aromatic yield is given by that, and it will depend on the NO2 concentration. And this is what we've got for 3-nitrotoluene from toluene. The shape of the curve is determined by the rate constants for the rate constant ratio, KNO2, the OH aromatic adduct plus NO2, and KO2, the OH aromatic adduct plus O2. And if I use the numbers from Cornelius-Zech's group and fit it with an alpha of 7.5, the alpha just moves you up or down, then you get that sort of fit. This is a log-log plot, which is sort of a bit hazardous. The uncertainty in the numbers, experimental uncertainty, is probably about a factor of 2. Down here, we were getting down to levels where we had real difficulties calibrating the instrument for 3-nitrotoluene, the way we do it. But anyway, there's a generally good fit. It's the lab data is clearly consistent with the chemical mechanism, or the mechanism, and with the kinetics from Cornelius-Zech's group. So it sort of looks all right. And you can also get the indication of this from the products formed from the O2 channel. As you increase NO2, they will change. They generally go down, or glyoxyl and methyl glyoxyl from toluene here decrease as you increase the NO2. And there's a dashed line there which uses Cornelius-Zech's rate constants, and the solid line is a fit with a rate constant ratio which would mean the two reactions of the adduct with NO and NO2 would be equal at 2.5 ppm of NO2 versus his would be at 3.3, and the two curves are indistinguishable. So it's not a particularly sensitive way of getting data, but you get some indication of 4 ppm NO2 is there. But what we see out of these is the values of NO2 in air, or mixing ratios of NO2 in air, at which the two pathways for the OH aromatic adduct would be equal. And for the monocyclic aromatics, i.e. all these guys up here, it's in the ppm range. And our numbers are the ones on the right-hand column from product studies, and they're not that accurate. I mean, there's significant uncertainties on them, but they're in the same range as what Cornelius Zetsch et al. Have seen. But the important thing is they're all in the ppm NO2 range. So, once you're down at ambient conditions, the adducts are going to go too. In contrast, naphthalene and the dimethylnaphtalenes, you're down in the few tens of ppbs, which are levels of NO2 that can be encountered, or close to levels that can be encountered in urban atmospheres. And biphenyl is essentially a phenyltoluene, is somewhere in between. And the other thing that's sort of interesting is the yield of alpha is about 10% for biphenyl and benzene toluene, and 1% or less for the naphthalenes. So this sort of simplistic reaction mechanism, given the nitro compound, and I left the water off on the right, but never mind, it clearly isn't quite the whole story. If this intermediate in the middle is thermalized, thermally stabilized, then the elimination of water is highly endothermic, and it's probable we're dealing with a chemically activated system, and we're only seeing a little bit of leakage through the system, essentially. But who knows? At least I have no idea what the other 90 to 99% of the products from the NO2 plus OH adducts give. So anyway, and if you look at the NO3 reaction, this is reaction on the face of it is very similar. Addition to the ring, or H atom abstraction, but the addition to the ring is reversible. And it looks like for the monocyclics that the NO3 aromatic adduct back decomposition is sufficiently fast that it overwhelms any reaction with O2 and NO2. And so all you see is the H atom abstraction pathway. So this one essentially flows only that way. So if you look at NO3 plus toluene, there's a significant kinetic isotope effect between toluene and toluene D3 or toluene D8, indicating that there's an H atom abstraction is the rate determining step. And so it all goes by the abstraction route. If you put the thing together, then you end up with a rate constant for these reactions, which has rate constant for the abstraction pathway plus a complex rate for the addition, which depends on the O2 and the NO2 concentrations. And if K NO2 times NO2 dominates over K O2 times O2, then it's going to be linearly dependent on NO2. And for naphthalene and for the alkyl naphthalenes we've looked at, and sort of part per million concentrations of NO2, the addition dominates over the abstraction, and the NO2 pathway dominates over the O2 pathway, and you get a rate constant which is linearly dependent on NO2. And that initially, many, many years ago, threw us for a loop, because that then looks like N2O5 kinetically. It's NO2, the loss rate is K times NO2 times NO3, and looks like N2O5. Right? It took us a number of years to figure out that it really was an NO3 reaction followed by NO2 reacting with the adduct. But anyway, so in this case, not only is the alpha the same, you've got the yield now depends on NO2, but the rate constant is also NO2 dependent. So the NO3 reaction, what you get, the two pathways for the NO3 aromatic adduct, are equal at about 100, sort of 100 ppb NO2. It's less than 80 for naphthalene, and we get values of 100 and about 300 for those other two. The other thing that's sort of interesting is that the yield is now much higher. Instead of being less than 1% from the OH aromatic adduct, we're up in the sort of 10 to 30+% for these NO3 PAH adducts. And as I mentioned, the monocyclics, benzene, toluene, xylenes, there's no addition pathway. It's all H atom abstraction. There's no nitro-aromatic formation. So we can try and put some numbers onto things. And the same grad student, Mariko Nishino, did a field study, or no, it wasn't exactly a field study, not by your definition anyway. She went out and measured these species, the PAHs or aromatics and the nitro-aromatics for 6 days in 2006-07 over a midday period about 10 to 4 p.m., 10 a.m. to 4 p.m. And they were all very similar each day, so I've just averaged the days. So the toluene concentration was about 1.5 ppb. Naphthalene was about a factor of almost 100 less. These are the nitro yields calculated at 20 ppb of NO2, which was the NO2 concentration. And you can see that even though toluene has a higher alpha at high NO2, the yield at 20 ppb is less than that of naphthalene. So you're further down on the curve. And OH rate constants are in there. Naphthalene is about 4 times more reactive than toluene. And put that together, the formation rates given there, 4 times 10 to the minus 5 ppb per hour for the nitrotoluene, and about 10 to the minus 5 or 9 times 10 to the minus 6 ppb per hour for 2 nitronaphthalene. I did this for 2 nitronaphthalene because 1 nitro is a potential direct emission. And then if you sort of look at the amount formed, that's given here, but you can sort of divide the amount formed by the formation rate to see how long you'd have to sort of accumulate it to get that amount. And it's 2 to 3 hours for nitrotoluene and about 1 hour for the 2 nitronaphthalene. 2 nitronaphthalene undergoes photolysis, lifetime of about 3 hours. So these numbers are essentially say that you can account for the amount observed in the ambient atmosphere quite readily. I mean, if these accumulation times had come out to be 1,000 hours, you'd have a real problem. But, you know, it's right in the park. One could say it's amazing. Might be one word. Fortuitous would probably be another. But anyway, so you can do similar calculations for the sort of relative formation rates of our 2 dimethyl nitro naphthalene markers that we had, one for OH, one for NO3, so 1,7-dimethyl 5-nitronaphthalene and 2,7,4. The parent PAHs are typically, or dimethylnaphthalenes, are typically present at fairly similar levels, and it's taken into account. So the relative formation rates at conditions representative of Mexico City, which was, I think this was in 2003, which was 40 ppb of NO2 while we had some students down there. So relative to one for this one, the 2,7-dimethyl-4-nitronaphthalene should be about 15 or 16 times lower in abundance. And in Mexico City, it was down by a factor of 6. Well, it looks, at least it's in the right direction and not too bad. And if I do calculations for nighttime formation, there wasn't any nighttime formation in Mexico City. It was dominated by OH, at least for the PAH reactions. But the system switches around, which is what we observe in ambient or in our chamber experiments. But the other thing, well, there's two take-home things on this, one of which is we can certainly predict the right abundance or relative abundance of these nitro-dimethylnaphthalenes, and the other is that the daytime formation of this one is reasonably similar to the nighttime formation of the other one from the NO3 reaction. So despite the fact that the NO3 reactions are a really minor loss process for these PAHs, the nitros can be formed in fairly significant quantities, at least relative to the OH. So the things all hang together. At least that's the good thing. I mean, if these had been 10 to the minus 5 or something, we wouldn't have been able to explain the nighttime observations. But they are in the right sort of magnitude. And you've already seen this, so we won't belabor it. The conclusions of this is that the nitro-aromatics are predicted to be formed essentially only in polluted urban atmosphere, because the formation yields depend on NO2, and for the NO3 reactions with the PAHs, the rate constants also depend on NO2. So as you dilute the system down, the formation yields just drop like a stone, and the NO3 reactions also slow down. And so now we're, for the first time, or at least we're now at the point that you can start putting these into predictive schemes. You can start putting these numbers, the rate constants that are around and the yields that are around, into sort of urban airshed models. You could start predicting nitro-aromatic formation. And the final one, which is obvious, is that decreasing ambient NO2 concentrations will decrease the formation rates of these nitro-PAHs and nitro-aromatics from gas phase reactions. And in this case, so this shows it graphically. This is the naphthalene system, this is the toluene system. So despite a higher yield at higher NO2s for the toluene system, at conditions close to ambient, which ambient is essentially right down in the weeds down here, the naphthalene is more effective at forming nitro-aromatics. And the one on the right shows that the yield, the rate constant also increases with NO2 by maybe a factor of 2 or 3 at conditions in polluted urban atmospheres. And again, you get the rapid fall off at low concentrations. And acknowledgements, same ones to some extent. This is really Janet Airy's, who happens to be my wife. It's her, really her field is the PAH field. I just do some of the lab experiments and get sent out to do some sampling, or I used to get sent out to do some sampling once in a while. And then the experiment was funded by the US EPA and California Air Resources Board at various times, and the people involved with these, Noriko Nishino, Lin Wang, and Katie Zimmerman, and some of the experimental stuff was done by Sarah Ashman again. And that's it. Thank you.
All right, I think we have time for 1 or 2 questions, if we have any.
Yeah.
Oh, hang on a second.
So you mentioned about an ubiquitous source of glyoxal in the 1,4-dicarbonyl work.
Well, no, it's the ubiquitous glyoxal. We nearly always see glyoxal in, if we do chamber experiments of almost any compound, there's nearly always some, maybe small, and I mean often quite small, but it's always there, nearly always there. And we often see methyl glyoxal as well. Now, these could be second or third or whatever generation products. Carry out the reaction to maybe 20 or 30% consumption of our initial compound. It's possible that some of the products have reacted, or we may be getting multi-generation products to some extent. Glyoxal's nearly always seen.
Okay.
You've probably seen the same in FTIR, right?
Yeah, we would. So yeah, a quick question about the mechanism for the 1,4-dicarbonyls. Yeah, do they kind of behave as predicted, like addition versus abstraction? Would you say, or?
Oh, it's largely OH addition.
Okay, yeah.
I mean, actually, no. It's a mixture of abstraction and addition.
For the aldehydes,
Yeah,
you get,
the aldehydes will undergo abstraction. There'll be a certain amount of addition. The addition is the double bond is deactivated somewhat by the carbonyl groups. So the ozone reactions are actually quite slow.
Right.
And the NO3, has anybody done NO3? I suspect they're quite slow as well.
Mm-hmm.
Well, no, the aldehydes will be fast enough, but the OH is a mixture of addition and abstraction.
So kind of like acrolein or
Yeah,
something.
Yeah.
and in
Very
fact,
similar.
we've looked at products from OH plus 3-hexene 2,5-dione, and in that case, it's all addition because it's a diketone. And the thing splits different to what one naively would expect. It doesn't cleave the double bond. I mean, it adds the OH and alkoxy, but then it kicks off a CH3CO.
Yeah, acetyl. Okay, yeah. It's a little bit like we were talking earlier about the isoprene secondary products.
Yeah.
Cool, thanks.
All right, any more questions? This will be the last one, right?
Have you looked at any of the products from like benzofuran or furan aldehydes? No.
All right, well, let's thank Roger one more time. Thank you.